How's it going?
Hi, how are you?
I am doing well. It is, it's Thursday, which is great. And we're here at an awesome community day, hearing from wonderful speakers like yourself and learning a bunch. I'm pretty excited. Yeah. So I guess I'll go ahead and introduce you. So for everyone watching, this is Haki Benita. He is
Hi,
a
everyone.
brilliant Postgres mind. I've learned a lot from him in his blog posts and things. So and as a fun way of kind of introducing you, you let us know that you are a big fan of cooking shows, but you do not in fact cook yourself.
Yeah, I can't cook anything. I just like to watch.
I mean, I get it though, because I feel like when watching cooking shows, I don't know, it's incredible what they're able to do, and I know that I would never be able to do most of what you know all
Yeah.
the delicious creations they're making. So
I'm being invited to friends' houses from time to time, and they cook. And I think that after eating a lot of my friends' cooking, I think most people are like me. They just don't know how to cook, you know?
so does that mean that your friends also that your friends can cook, or are you hacking them for not? No, I'm kidding.
No, I think that they just like watching cooking shows, and they
Yeah.
are better off doing takeaway,
Yeah, no, I get it. I get it. I mean, I definitely feel that.
Yeah.
So yeah, thank you so much for joining us for doing your talk. Super excited about the SQL tricks. Yeah, and I'll just let you go ahead and grab the stage because I know you have lots to cover.
Okay. Yeah, lots to cover. So first of all, my name is Haki Benita. I'm a developer. I'm a DBA, and I'm interested in a lot of stuff. Today, I want to talk to you about some tricks that I've learned along the way as an application DBA. So before we start, I just want to make this distinction between two types of DBAs. I think that most people find this very useful to know exactly what type of DBA they are. So back in the day when you had to install your own database and you had to configure storage and backups and disks and so on, this today for me is called an infrastructure DBA job. Now, the other part of a DBA job is usually more related to the actual application, which involves schema design, tables, indexes, performance, and implementing all sorts of processes for BI and different ETL processes and so on. So and most of the jobs I've done in my years is an application DBA. So we are going to focus on the right part of this slide, the application DBA. So the first thing I want to talk about is one of the most common misconceptions that I see about SQL, and that's that indexes make any query faster. So just to illustrate, let's imagine this user's table is pretty simple: ID, email, and an indication if the user activated the account or not. Okay, so we have 1 million users in the table, and our users are good users, and most of them activate the account. We send them an email, they click the link, and they activate the account. So we usually want to query the activated users because these are the users that interact with our application. So we must have an index, right? This is the first thing that comes to mind. So let's try and create this index and then query for activated users. We can see that we query for activated users, but the index is not being used. Postgres decided to do a sequential scan on the user's table. That's a full table scan. So if we try to query an activated user, a specific activated user, the index once again is not being used. So if on the other hand, we try to query inactivated users, that's users that did not activate their account, that's the 1%, we see that Postgres did decide to use the index. You can see in the execution plan that Postgres did what's called an index scan with the index we have on the activated column. So why is that? Okay, why is index not always the best plan? Let's consider these facts on the table. So first, the size of the table is 65 megabytes. Okay, we have 1 million users, and the size of the table is 65 megabytes. The size of the B-tree index that we created on the activated column is 7 megabytes in size. So just imagine that. If I told you that you are going to read the entire table, 100% of the table, would you read the index as well? I'm guessing not, okay? What if I told you that you're going to read 99% of the table? How about 90% of the table, even 80% of the table? Would you use the index? So Postgres actually maintains statistics on our tables to help him decide exactly what is the threshold after which it's a good idea to use the index to evaluate some condition. So if we used the table pgstats and get some useful statistics on this column activated in the users table, we can see some of these statistics that Postgres is using. The first one is how many distinct values we have for this column. So this is a Boolean column, so we have two distinct values, true and false. Next, Postgres maintains a histogram of the most common values, and for each value keeps the frequency. So in this case, Postgres know after analyzing the table that 99% of the values for this column contains the value true, and the rest, which is slightly under 1%, contains the value false. So Postgres is smart enough to use these statistics in order to determine how to access the table. So when we query the activated users, which Postgres knew are roughly 99% of the table, Postgres decided to do a full table scan. On the other end, when we queried for inactive users, which Postgres knows after analyzing the table that are roughly 1% of the table, Postgres decided to use an index scan. Okay? So that's pretty useful to know, and you can keep track of these stats. So what if we actually do need to query inactive users a lot? We just saw that this index might not be as useful most of the time, but what if we actually do need to query inactive users? So we know that Postgres will not use the index to query activated users, the 99%, but what if we can just not index them? This is where a very, very handy feature of PostgreSQL comes in very, very handy, and that's partial indexes. You can see in this example that we only want to query users that are not activated. So what we can do is we can create an index on the users table, the ID column, but only for rows where the user is not activated. Now, if we try to use this index to query for inactive users, we can see that Postgres is using this index, but that's not all. We can also query for specific users because we indexed the ID column, and you can even see that Postgres, once again, is using the index. But the big advantage of using partial indexes is that they are very, very small. As an example, in this case, the full index was 7 megabytes, and the partial index was only 232 kilobytes, which is way, way, way smaller. And the bigger the table, the bigger savings are on partial indexes. Now, I'll just note that if you're using Postgres earlier than 13 without deduplication, the index on the activated column is actually 21 megabytes. So I'm not going to go into that, but partial indexes under 13, are even a bigger saving. Okay, so whenever I need to explain to my mom what I'm doing, she has no idea what a DBA is, and whenever I try to explain, it's very, very hard. So at some point, I just started saying, okay, like a plumber, so I move data around, just like a data plumber. So a big part of an application DBA job is to move data around. So let's look at some examples of how we can optimize moving data around. consider this example. This is a very, I would say, common example. You have a product, you have a customer, and when a customer purchases a product, you have a sale, okay? So this is the schema here. So let's say that we want to normalize the emails in our customer table. Let's say that our application did a pretty lousy job at optimizing emails, and we have mixed case, we have uppercase, lowercase, and so on, which makes it very, very difficult to search for emails. So we want to make sure that all the emails are lowercase. So I'm guessing that most people would just do that, right? Update the customer table and set the email to lower email. We can see that all of the rows in the table are updated, and it took roughly 1.5 seconds. Now, what if we instead only update the rows that actually needs updating? This is the exact same update, but this time we are only updating emails which are not already in lowercase. So now, instead of updating all of the table, we just updated 10,000 rows, and that's significantly faster. Okay, so if you want my rule of thumb, whenever you have an update, usually you want to make sure that there's always a where clause to make sure that you don't update rows that don't need updating. That's a good rule to follow, and that's very common in bulk updates, data migrations, and my personal favorite, quick fixes in production, where you SSH and just update and you lock the entire table. Okay, so let's talk about constraints. Constraints are great. Constraints are amazing. Use constraints, okay? But you need to use them smartly. First, if we take our schema and we start adding constraints, first we add a foreign key from sale to product, and then from sale to customer, and then we create an index on the creation date of the sale. This is pretty fast, right? Great. Next, we want to load some data into the table. So we just do an insert. In this case, I'm using random data, but in your case, this can be an actual data. Maybe you are loading this from, I don't know, some CSV, some remote system, whatever. This takes, in this case, 15 seconds to load 1 million rows into the sale table, okay? So we added the constraints and then loaded the data into the table. Now let's do it again, but this time we are going to do it backwards. Instead of adding the constraints and then loading data into the table, we are going to load data into the table. You can see that before it took 15 seconds and now it takes only 2, but we still need to add the constraints. This time, adding the constraints is significantly slower, but if we look at the overall process, when we added the constraints and then loaded the data, it took 15 seconds. When we did it backwards, when we loaded the data and then added the constraints, it only took 2.2 seconds. So that's 6 times faster. So when you need to load a lot of data into a table, you should consider dropping and recreating the constraints after you loaded the data. This can make things very, or much faster. Okay, so now let's load data again into the table. And this time we are loading 100,000 rows into the table, and we are generating sales for a period of 2 years. 365 times 2 multiplied by day from 2020. So we have sales from 2020 all the way until 2022, okay? And now we want to find all the sales that were created in the first 10 days of May. So we get this execution plan, okay? And we can also see that Postgres used an index. It did a bitmap index scan on the sales table using the sale created index. So I'm guessing that at this point, probably, I don't know, 99% of the developers would say, that's great, the index is being used. But in fact, that's not the best plan you can get. This is a good point to stop and talk about correlation. So correlation is a concept that takes some time to sink in, but I'm going to try and demonstrate it, okay? So correlation is the statistical correlation between the physical row ordering and the logical row ordering of column values on the disk. So imagine that you have a table, and that's very common when you have time series. Say that you have a table that you only insert data into, okay? And you have a column for the timestamp. And every time you insert a row, you use the current date. Maybe it's a sensor data that you keep inserting and inserting. In this case, as you add data into the table, the date column is slowly incrementing, and you're always adding data at the end of the table. So in this case, consecutive values of the date are going to be next to each other in adjacent pages on the disk. So in this case, you have perfect correlation, right? Because there's a perfect correlation between the logical value of the timestamp and the position on the disk. However, if consecutive values are scattered all across the table, then your correlation is going to be close to zero, okay? Just to understand, if you are adding values in descending order, the correlation is going to be -1. So there are some types of data which are naturally high correlation, and auto-incrementing IDs and timestamp in an append-only table, as we just mentioned. These types of columns usually have high correlation. So once again, Postgres maintains this statistics on our table. It's called correlation, and we can get it from pgstats. Okay, we can query. In this case, I want to see the correlation for the ID column, which is an auto-generated primary key, and the created at column, which is the timestamp. In this case, I inserted data randomly into the table. So the ID, which is auto-generated, has perfect correlation because it was generated automatically, but the creation date was generated randomly. So it has very, very low correlation, meaning adjacent pages contain completely different values of this timestamp. Now, just to demonstrate the effect of correlation on performance, let's do the exact same thing, but this time we are going to insert the data and order it by the creation date. Okay? This is the exact same insert statement. The only thing that I added was this order by clause. So if we run this insert and once again look at the stats, we can see that the creation date, the created at date, now has perfect correlation, and that's because I inserted in a sorted way. Let's run our query again. We are looking for all the sales that were executed, created between the 1st of May and the 10th of May. And we can see that now Postgres is doing an index scan, and it's much faster. So before we had a bitmap index scan, and now we have an index scan. And the reason for this change is the correlation. To understand why, we need to understand exactly what a bitmap scan is. So when Postgres thought that we have values scattered all across the table, he worked in 2 stages. The first stage was to go over the index and collect all the references to the pages that contain relevant rows. Only after it got all of the pages that it needs to access, he accessed the pages in the table, okay? But once the correlation was perfect, Postgres just figured that if he gets one value, it's very likely that consecutive values within this range are going to be in the same page. So this is the difference. When we had very low correlation, Postgres used bitmap index scan, and it took almost 3 milliseconds. When we had perfect correlation, Postgres used an index scan, and the timing was much lower. So you need to keep in mind, the next time that you are loading a lot of data into some table, you should sort it in a way that can benefit range scans on the table, okay? Now, if you already have a table that is not sorted on disk, maybe you find that some key columns have very, very low correlation. You have several options. One of them is the cluster command. you should be careful because this is a blocking operation. It takes up a lot of space, and it also affects the correlation of other columns. You can also do it without any downtime using the pgrepack package, but you should just avoid this problem by loading data sorted when possible. So we can't talk about correlation without mentioning my personal favorite type of index, and that's the block range index, or BRIN. So BRIN works by keeping a range of values within a number of adjacent pages. Now, I know it sounds complicated, but we're going to see a demonstration. So let's take this as an example. Say we have the values 1 through 9, each in a single table page. Now we want to index these values using a BRIN index. So this is what BRIN index does. First, it divides the table into ranges of 3 adjacent pages. Okay, this is a parameter. In this case, we're using 3. So 1, 2, 3, first range, 4, 5, 6, 7, 8, 9. And this is the BRIN index. For each range, the BRIN index will keep the minimum and the maximum value in this range. So this is the BRIN index, 1, 3, 4 through 6, 7 through 9. Okay? Now, let's try to use this BRIN index to search for the value 5. So when we look at the first range, the BRIN index tells us this range contains values 1 through 3. So 5 is definitely not here. The second range, 4 through 6, 5 might be here because 5 is between 4 and 6. And the final range, the last range, 7 through 9, 5 is definitely not here. So using the BRIN index, I know that I can look for the value 5 only in these 3 blocks, 4, 5, and 6. So using the index, I was able to minimize the number of pages I need to read. Instead of reading the entire table, which is 9 pages, I can just read 4, 5, and 6. Okay? Now, why is this correlation so important to BRIN index? Let's look at the exact same values, but this time they are not going to be sorted nicely on disk. So once again, we take 3 adjacent pages, we divide the pages into 3 ranges, and we take the minimum and the maximum in each range. Okay? Now let's try to use this index to query for the value 5. 2 through 9, 5 might be here. 1 through 7, 5 might be here. 3 through 8, once again, 5 might be here. Notice that it's not necessarily there, but it might. So in this case, the index is completely useless because 5 can be in any of these ranges. So the BRIN index was unable to minimize nothing. I still need to read the entire table. This is why correlation is so important to BRIN index. So if you want to create a BRIN index, you can use create index using BRIN. And this is a very important parameter. This is pages per range. In our example, we used the 3 because we grouped 3 adjacent pages into one range. The default is 128. The smaller this number is, the more accurate and the bigger the index is. And the lower, the bigger the index and less accurate the index is. So just to compare BRIN with B-tree, if we use a BRIN index on the created column, the index size is 48 kilobyte. If we use a B-tree index, which is the default, it's almost, it's more than 2 megabytes. So for very, very large tables, BRIN can provide a very good solution. And since we are on the subject of time series, if you have an append-only table and you need to index the time column, then BRIN is a very good choice in some cases. Okay, almost done, promise. Just a few more tricks and I'm done. So if you're not aware of that, then Postgres has this thing called the write-ahead log. This is something that every change you make to the data is written to this write-ahead log. So the while is used to maintain integrity, recovery, and also used for the replication mechanism in Postgres. So writing to the while is very important, but there are some circumstances where you can disable it to make things faster. One example that I run into very often is intermediate tables. These are the type of disposable temporary tables that you use in the process of doing something else. For example, maybe you have a migration, maybe you are loading data, copying data into the table, and then triggering some kind of ETL process. So you can make things faster by making the table unlogged. So you just need to remember that if your database crashes and you need to recover, then there will be nothing in this table. And if you have replications, the table would not be replicated. But if you're just using that as a temporary table for some process, then maybe it's fine and you can make things a bit faster. Another cool feature that I think not a lot of people are aware of, or maybe they are aware of it, but didn't really consider it like a feature, is what I call invisible indexes. Sometimes you have an index and you're not sure if it's really achieving its goal, if it's really making things faster, and you want to see what an execution plan may look like without the index. Now, in other databases, you might use hints for that, but Postgres doesn't have hints. So what you can do is you can actually drop the index in a transaction, do whatever you want to do, and then roll back when you're done. Okay, so this is using a very cool feature of Postgres, which is called transactional DDL. If you are coming from other databases, for example, Oracle, you might think that when you execute DDL, it terminates the transaction. But in Postgres, DDL statements are also can be executed inside a transaction. So, for example, I can open a transaction, drop an index, produce an execution plan, and you can see that the index is not used. And then when I roll back, it's like nothing ever happened. So this is what I call invisible indexes. And I think that I'm almost out of time, and this is my final thing to say. So if I told you that you need to execute something at night and you need to pick a time, I'm guessing that most of you will pick 1 a.m., 2 a.m., 3 a.m. Maybe you'll choose 2:30 a.m., 3:30 a.m. Maybe you're super creative and you're going to go for 2:17 or 3:14, right? So developers, when they need to schedule long-running processes, we usually do it at around hours. Okay, if you look at a low chart of a database at night, you can sometimes see like these spikes at round hours. So what I'm saying is, be smarter. If you need to execute something in the middle of the night, you have a better chance of finding a system at rest if you schedule it at another time. So the next time you need to schedule something in the middle of the night, do it at 3:48 or 2:15 or 1:14, something like that. And then maybe it will make things easier for you. So this is it. So you can check out my blog. You can find me on Twitter. You can subscribe to my stuff here. And if you have anything you want to say to me personally, and none of these platforms suits you, you can just contact me in this email address. And that's it.
This was awesome. I know that I got a lot of great tricks that I did not know before. So this happens every time that you I read your stuff, or I always learn something. It's awesome. So we have a few pretty good, we have two good questions, and we want to give you the option for which one you would like to talk on, because we only really have time for one question. So would you like to talk about a copy and constraint question, or UUIDs and stat correlation?
UUID and correlation. Well, UUID are random by nature, so naturally they're going to have very low correlation. However, there are some interesting developments regarding UIDs, which I don't know, happen to have some experience with lately. There's a new type of UUID called UUID6. I think it's in RFP right now. And UUID6 is time-aware UUID, meaning that if you're using UUID6, it's going to, the prefix is the date. So it's going to also have natural correlation if you use the primary key. There's also other implementations of UUID which are also prefixed with the date, which makes it a great candidate for primary key and also maintains some element of time where you can keep the correlation high. So that's a really great question. Seriously, great question.
Yeah, thank you.
Right on the spot.
Yeah, I'm sorry if I mispronounced your name, but Watts, thank you for that awesome question. And also, David White, we will make sure to get an answer for the copy and constraint question as well. But yeah, thank you so much, Haki, for coming on and giving us these wonderful nuggets of wisdom. They are super useful.
Thank you all. Have a great day.
Yeah, you as well. Thank you so much. This is awesome.
Great. Bye.